Welcome back. Now we are going to study types of polymerization reaction. There are two types of polymerization reactions. First one, addition or otherwise called chain growth polymerization. Second one, condensation or step growth polymerization. We can start with addition polymerization. In this polymerization, the monomer used are unsaturated compounds, that is, it contains either double bond or triple bond, and doesn't matter whether we are using same type of monomer or different type. This mode of polymerization leads through the formation of either free radical or ion species. Out of these, free radical mechanism is most common for addition polymerization. Free radical mechanism. A variety of alkenes or dienes and their derivatives are polymerized in the presence of free radical generating initiator like benzoyl peroxide, acetyl peroxide, tertiary butyl peroxide, etc. This mechanism follows three steps. First one, chain initiating step. Second one, chain propagating step. And the third one, chain terminating step. I'll explain the mechanism with an example, that is formation of ethene to polythene. On heating or exposing to light a mixture of ethene with a small amount of benzoyl peroxide initiator, generation of phenyl free radical is taking place. In benzoyl peroxide, the oxygen-oxygen bond breaks homolytically to form two phenyl free radical. This phenyl free radical on adding with ethene forming a much larger free radical. This step is called chain initiation step. As this free radical react with another molecule of ethene, another bigger sized free radical is formed. This process will continue to form new and bigger free radical, and this step is known as chain propagating step. When this bigger free radical react with another free radical, polymerized product is formed. This step is called chain termination step. For termination of a long chain, these free radical can combine in different ways to form polythene. One mode of termination is combining two similar free radicals to form a very large polymer. In the polymerization of ethene to polythene, we are taking benzoyl peroxide as the initiator or as a catalyst. So we have to start from benzoyl peroxide. So in a mixture of, we are taking a mixture of benzoyl peroxide and ethene molecules. Here we have more number of ethene molecules than benzoyl peroxide. So benzoyl peroxide is C6H5CO, C double bond O, C double bond O, C6H5. This is the benzoyl peroxide. On heating or exposure to light, cleavage, this oxygen-oxygen homolytic cleavage take place so that each species get one electron. Okay, so we can write C6H5, C double bond O free radical, and here also C6H5, C double bond O. So two free radicals are obtained, and this is a very reactive species, and it react itself and break this bond, CC bond, and you are getting two C6H5 free radical, C6H5 free radical. This is nothing but phenyl free radical, plus you are getting this one now. Here homolytic cleavage, so here also one electron, here also one electron. So you are getting C double bond O, here one electron, here also one electron. These two electrons make a bond, and you are getting here also two, no, C double bond O, double bond O. This is your carbon dioxide. Okay, so you are getting carbon dioxide here. Okay, and the reacting sample having ethene also, no, this react readily with ethene. C6H5 free radical react with ethene molecule readily. So what will happen? This bond break homolytically, the double bond, and two carbon atom get one electron, and this electron and this one electron from the phenyl free radical join together to make a bond. So you are getting C6H5 single bond, CH2 single bond, CH2 free radical. This step, this all together we are saying it as the first step, that is chain initiation step. Okay, and the second step, starting with the free radical obtained from the first one now. This is the free radical obtained. So I am writing this again, C6H5 CH2 CH2 free radical. Free radical we have to write here. Okay, starting from there. Okay, it again react with the another ethene molecule. Okay, what will happen? This again the double bond breaks, and here both carbon atom get one electron, and this electron and the electron from this carbon atom make a bond, and you are getting a compound like C6H5 CH2 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 free radical. A lengthier one you got, no? A bigger free radical. Suppose that we are taking n number of ethene molecule. What will happen? Instead of writing like this way, you have to write n here. So n molecules will be present here, and you are getting a very long free radical. Okay, this is the second step, that is chain propagating step. And the third step, what is the third step? When any free radical, any two free radicals comes together, then it combine together to make a molecule, not a free radical. Okay, suppose that so many polymerization taking place in the same sample, so we will have so many free radicals also. So suppose we are having C6H5 CH2 CH2 n time CH2 CH2 free radical is there. Suppose that, okay, let me write it clearly. CH2 free radical. So here two electrons are there now in the free radical. They join together to make a bond. So you are getting bond like this way. Let me write this: C6H5 CH2 n times CH2 this join with this one, so make a bond CH2 then CH2 n times C6H5. This I am writing like this way, but it is a long chain. Okay, you cannot see now. Now you can see, no? This is a long chain because I have no space for writing it in a straight way, so I am writing like this way. Okay, this is the third step, that is chain termination step. Okay, clear, no? Next topic, preparation of some important addition polymers. Polythene. There are two types of polythene, low density polythene and high density polythene. Low density polythene is obtained by the polymerization of ethene under high pressure of 1000 to 2000 atmospheres at a temperature of 350 Kelvin to 570 Kelvin in the presence of trace of dioxygen or a peroxide initiator. Low density polythene obtained through the free radical addition and hydrogen abstraction has highly branched structure. The low density polythene is chemically inert and tough but flexible and a poor conductor of electricity. Hence, it is used in insulation of electrical wires and manufacture of squeeze bottles, toys and flexible pipes. High density polythene. It is formed when addition polymerization of ethene take place In a hydrocarbon solvent in the presence of a catalyst such as triethyl aluminium and titanium tetrachloride, that is Ziegler-Natta catalyst, at a temperature of 333 Kelvin to 343 Kelvin and under a pressure of 6 to 7 atmospheres. High density polythene thus produced consists of linear molecule and has high density due to close packing. It is chemically inert and more tougher and harder. It is used for manufacturing buckets, dustbins, bottles, pipes, etc. Teflon, polytetrafluoroethene. Teflon is manufactured by heating tetrafluoroethylene with a free radical or persulfate catalyst at a high pressure. It is chemically inert and resistant to corrosion and is used for making oil seals and gaskets. It is also used for making non-stick cookwares. The tetrafluoroethylene, that is CF2 double bond CF2, on polymerization in presence of catalyst and at a high pressure, you are getting Teflon. Next one is polyacrylonitrile. The addition polymerization of acrylonitrile in presence of peroxide catalyst lead to the formation of polyacrylonitrile. CS2 double bond CHCN, that is acrylonitrile. On polymerization in presence of peroxide catalyst, you are getting polyacrylonitrile. It is used as a substitute for wool in making commercial fibers as Orlon or acrylan. Next category, condensation polymerization or step growth polymerization. In this type of polymerization, condensation reaction between two bifunctional monomers taking place repeatedly. This reaction happens by the elimination of simple molecules such as water, alcohol, etc. In these reactions, the product of each step is again a bifunctional species and the sequence of condensation goes on. Since each step produces a distinct functionalized species and is independent of each other, this process is also called step growth polymerization. The formation of terylene or dacron by the interaction of ethylene glycol and terephthalic acid is an example of this type of polymerization. Here in ethylene glycol, two OH groups are there and phthalic acid, terephthalic acid, carboxylic acid group, two carboxylic acid groups are there. And here condensation reaction taking place. How it happens? Here OH from this carboxylic group and H from this glycol eliminated as such when it combined together. So elimination of water molecule taking place and you are getting OH, CH2, CH2, O, then CO means C double bond O, no? C double bond O, OOH. You are getting like this as this product. Okay, but if we are having n molecules, for polymerization we need n molecules. No, here also n number of water molecule is eliminated and you are getting a product like here also OH minus OH will be eliminated and you are having C double bond O with a bond and here also O will be there, H is eliminated and this is the repeating unit and this is called terylene or dacron. The polymer is called terylene or otherwise called dacron. Okay, clear no? The reaction condition is at 420 to 460 Kelvin in presence of zinc acetate antimony trioxide catalyst. Now we can discuss some condensation polymers. First one, polyamides. These polymers possessing amide linkage, that is CONH linkage, are important example of synthetic fibers and are termed as nylons. So we can study the preparation of nylons. First one, nylon 6,6. It is prepared by condensation polymerization of hexamethylenediamine with adipic acid under high pressure and at high temperature. Adipic acid plus hexamethylenediamine giving that is at high pressure and high temperature you are getting nylon 6,6. Here elimination of water molecules taking place, and OH from acid group and H from amine group is eliminated as water. Nylon 6,6 is used in making sheets, bristles of brushes and in textile industry. Next one, nylon 6. It is obtained by heating caprolatum with water at high temperature. Caprolatum is a cyclic compound with amide linkage. On heating this caprolatum in presence of water, you are getting nylon 6. Nylon 6 is used for the manufacture of tire cords, fabrics and ropes. Polycondensation of dicarboxylic acid and diol, you are getting polyesters. Dacron or terling is the best known example of polyesters. It is manufactured by heating a mixture of ethylene glycol and terephthalic acid at 420 to 460 Kelvin in presence of zinc acetate antimony trioxide catalyst. Dacron fiber is crease resistant, that means wrinkle free, and is used in blending with cotton and wool fiber and also as glass reinforcing materials in safety helmets, etc. Third one, phenol formaldehyde polymer, that is bakelite and related polymers. Phenol formaldehyde polymers are the oldest synthetic polymers. These are obtained by the condensation reaction of phenol with formaldehyde in presence of either an acid or a base catalyst. The reaction starts with initial formation of ortho and para-hydroxyphenol derivatives, which further react with phenol to form compound having rings joined to each other through CS2 group. And the product obtained is called Novolac, and which is used in paints. Novolac on heating with formaldehyde undergo cross-linking to form an infusible solid mass called bakelite. It is used for making combs, phonograph records, electric switches and handles of various utensils. Next one, melamine formaldehyde polymer. Melamine formaldehyde polymer is formed by the condensation polymerization of melamine and formaldehyde. Melamine, when treating with formaldehyde, you are getting resin intermediate, which on polymerization, you are getting melamine polymer. It is used in the manufacture of unbreakable crockery. Next category, copolymerization. Copolymerization is a polymerization reaction in which a mixture of more than one monomeric species is allowed to polymerize and form a copolymer. The copolymer can be made not only by chain growth polymerization but also by step growth polymerization. It contains multiple units of each monomer used in the same polymeric chain. For example, a mixture of 1,3-butadiene and styrene can be formed a copolymer. 1,3-butadiene, N molecule of 1,3-butadiene treated with styrene, N molecule of styrene, you are getting butadiene styrene copolymer. This is nothing but your Buna S. Copolymer have properties quite different from homopolymers. For example, butadiene styrene copolymer is quite tough and is a good substitute for natural rubber. It is used for the manufacture of auto tires, floor tiles, footwear components, cable insulations, etc. Hope you understand this much. In the next video, we can study about rubber and biodegradable polymers. Thank you for watching and have a nice day.